Hello and welcome to our session today. It's going to be on persistent storage of Windows workloads in Kubernetes. My name is Anusha, and presenting with me is Jean.
Hi, everyone.
Two of us are software engineers. Before I get started, looks like it's a cozy, small audience, so maybe we can come closer so that we can focus. I mean, or there's plenty of room in the front, so. The agenda for today, we're going to start with talking about persistent storage in Kubernetes. This is going to be an OS agnostic section. We'll talk about how Kubernetes handles persistent storage in general. After that, we will move into the current state in Windows. In this section, we will talk about the different storage interfaces that work with Windows today. And we will also have a couple of live demos where a stateful application such as SQL Server can be used to provision volumes, can be used with persistent volumes in the backend. Finally, we'll wrap up the talk with some of the work we've been doing around CSI plugins. CSI stands for Container Storage Interface. CSI plugins for Windows. First, let's talk about persistent storage in Kubernetes. You might have seen this architecture diagram before, but just to recap, on the top, you see the Kubernetes master. Right now, this is a Linux node. The Kubernetes master manages the workers. The workers can be a mix of both Windows workers and Linux workers. The Windows workers need to be 2019, Windows Server 2019. At this point, I'd like to point out that Kubernetes version 1.14 provided GA support for Windows workers. Now, at the bottom of the diagram, you see the network and the storage fabric that are required for the cluster. This can be both on-prem or on the cloud. Looking at the master components, you have the Kubernetes scheduler, the API server, as well as a bunch of controllers that work together. We'll talk about the controllers in a bit. At the bottom, you actually see the components that are part of a worker node. This is typically the kubelet, the kube proxy, and the different plugins, the CNI, CSI, and CRI for network, runtime, and storage plugins. Now, notice that the Kubernetes master components are cluster-wide components that work throughout the cluster and doesn't have any OS-specific components. All the OS-specific components come down to the worker nodes. Looking at the components that are specific to storage, there are controllers that are running as part of the master that work together to provide persistent storage for Kubernetes. A controller in Kubernetes is basically a software loop that looks at the current state of the cluster and tries to converge that with the desired state of the cluster. The desired state of the cluster is typically provided by the user or operator in the form of a YAML file. And the controllers that work for persistent storage are typically the PV controller or the persistent volume controller, which is in charge of creation and deletion of persistent volumes. Attached controller, which is in charge of attaching these created volumes to the nodes in the cluster. And the node controller, which is responsible for working with the attached controller to move the volumes alongside the pods when the pods get rescheduled. Moving on to OS-specific logic in the worker nodes, we have the kubelet. The kubelet does a lot of the heavy lifting around mounting and unmounting volumes on worker nodes. And it has a lot of OS-specific logic. Container runtimes, like Containerd or Dockerd, that has a lot of OS-specific logic as well. And finally, Flex Volume and CSI plugins have node-specific attach operations as well as mount-unmount operations. Now let's look at some storage concepts in Kubernetes before we go further. These are basically like building blocks that Kubernetes overall uses to provide persistent storage. Pods, as we all know, are basically a set of running containers that represent your workload. A persistent volume claim, or PVC, is basically a request from the user to access a piece of storage in your cluster. And just like how pods consume CPU and memory, PVCs consume storage. And just like how pods can specify number of CPUs and amount of memory, PVCs can specify how much storage they need and what access modes they need it in. And typically, a pod will reference a PVC. Now, what happens when a PVC gets submitted to the Kubernetes master API server? There is some magic that happens, and a piece of storage gets provisioned behind the scenes. That piece of storage is actually represented in Kubernetes as an API object called persistent volume. And this PV, or persistent volume, is bound to the PVC, the claim that we just made. So they're married together. It's a one-on-one mapping. The lifecycle of a PV is independent of the lifecycle of the pod using it. Looking at the life of a PV, this is a very generic diagram of how the volume's lifecycle. You have the storage service on top and the pod consuming it in the bottom. So the volume gets created, it gets attached to a specific node when the pod gets scheduled on a specific node. Once it gets attached to a specific node, the pod actually will be able to mount that volume and start using it. When the pod is done with it, it can actually, the volume gets unmounted. When the pod gets rescheduled to another node, the volume will get detached from this node and reattached to another node. And eventually, when the volume is not used anymore, it can either be deleted or recycled or retained. Let's look into PV provisioning. Provisioning is basically a fancy word for creating or allocating volumes. And there are two types of provisioning that are supported in Kubernetes, static and dynamic. Static is basically creation of these persistent volumes up front. You have a pool of persistent volumes, and then when the user makes a claim, the controller sort of matches the claim with the existing PVs that are available, and the PV and PVC are bound from then on. And then the pod can basically come in and use it, mount it, and so on. The other way of provisioning is dynamic provisioning. In this, it's basically a on-demand provisioning of PVs. So when the user submits a claim is when the PVs get provisioned in the backend. This is definitely the recommended way because it's on demand. You don't have to create it ahead of time, and you also know what the user's specifications are. You don't have to sort of guess on your capacity or the request that is made. Now, the dynamic provisioning is done through a concept of storage classes. It's basically our storage classes are nothing but tiers of storage that are available in your cluster. So a storage admin comes in and creates different tiers, typically based on performance, some SLA requirements, and so on. And the storage classes are backed by, always backed by a provisioner. What is a provisioner? Provisioner is nothing but a piece of software that's constantly listening on incoming persistent volume claims. And if there is a match to itself, then it basically creates the persistent volumes in the backend appropriately. Let's look at the state of state in Windows, which is essentially what this talk is all about, with that in the background. So to understand that, let's look at what are the different storage interfaces available today in Kubernetes. We have entry plugins, which are basically plugins that are available as part of Kubernetes tree and run in process with Kubernetes core components. Then we have flex volume plugins, which are basically out of tree from Kubernetes and takes care of some customization on the worker nodes, typically on mount, unmount, and attach, detach. This is basically a host-based exec model approach for flex volumes. External provisioners live out of tree and out of process from Kubernetes, and they take care of the provisioning aspect of it. So the create delete of the volumes is handled by external provisioners. And finally, CSI is again out of tree and out of process from Kubernetes, and it manages the entire life cycle of a volume. So it's create delete, attach, mount, unmount. And there are more customizations that are coming in for CSI. Now, quick pros and cons table. The advantage of in-tree is basically you don't have to do any extra installation. The disadvantage is that it's all the in-tree plugin work is tied to Kubernetes releases. So if you have a bug or a patch release that you want to actually make to your in-tree plugins, you have to wait until the next patch of Kubernetes is out. The future is superseded by CSI. External provisioners, the advantage is that you can highly customize the provisioning aspect of it. But the disadvantage is that it's limited customization for the attach and the mount operations. Flex volume, you can actually customize the code for attach and mount operations, but you cannot customize it much for provisioning. And also in flex volumes, the idea is there is expectation, there are certain assumptions that are being made as far as scripts or binaries to be existent in your nodes at a certain location and so on and so forth. So the portability of this model is very limited. For that specific reason, flex volume is actually deprecated in Linux. It's still used in Windows because there is no better alternative for Windows, and we will see why in the later half. And finally, CSI. The advantage is that it's highly customizable. Almost all of the operations can be customized. And it's an industry standard. So CSI can be implemented in other container orchestrators like Mesos and Cloud Foundry, and the same storage plugin can be used across all container orchestrators if they adhere to the spec. So it's an industry standard, which is a great thing. But the disadvantage is, of course, there is the minor disadvantage, which is you got to install Kubernetes, and on top of that, you've got to install, maintain, and configure your CSI plugins on top of it. But this is definitely the future. Now, what are some of the considerations specific for Windows as far as writing a plugin goes? Now, disk device enumeration and volumes enumeration interfaces on Windows are very different from that of Linux. In Linux, all the devices and volumes end up as a file on your file system. But on Windows, they are all object-based. So you have to make Win32 calls to get the enumeration done, and it's not like you can actually read files off of your file system. So if you're a plugin author, you have to make that, take that into account. As far as the actual file system support goes, in Linux, you basically, for block devices, you ended up having ext234 or XFS. On Windows, you're going to have NTFS. For shared storage, in Linux, we have support for NFS. On Windows, we don't have support for NFS, and it's something that has been talked about for the future. But for right now, we have Samba support. And Windows also ends up having to heavily depend on PowerShell commandlets and scripts for many of the actions that need to be customized. Now, what's available today for in-tree storage for Windows? So kubelet.exe on Windows basically supports partitioning and formatting using NTFS. It also provides support for linking host volumes into the container. So this is similar to, there is a tool called MakeLink that is actually being used for this specific linking. This is similar to bind mounting on Linux, where you can bind mount something from the local host onto your container file system. Linking Samba shares to the containers file system is also supported. So with these features, it's actually possible to provide some pretty good in-tree support. So today we actually have file-based cloud volumes on Azure file through Samba. In fact, our demo is going to be that. Block-based cloud volumes support is also available on both Azure Disk and GCE PD. On AWS EBS, it's a work in progress. And for iSCSI, in-tree support is actually work in progress. It's targeted for Kubernetes 1.16. A quick diagram about the in-tree plugin architecture. So here we see that the PV claim actually comes into the API server, and it gets dispatched from the controller to the different in-tree plugins that are available. So basically, there is a inspect of the incoming claim, and the correct in-tree plugin is basically looked up and dispatched to. For create, delete, and attach, detach volumes, those components reside in the master. For mount and unmount, the kubelet takes care of it. The main point to drive home from in this picture is that all of the operations are happening within this blue box, which represents the core components of Kubernetes. So there is no call outside of the processes, the core KubeCon processes for in-tree plugins. Now we will look at the in-tree storage with Azure file demo. Here I have a 3-node cluster with 1 master and 2 workers. Both workers are Windows 2019. This is on Azure AKS service. I'm using AKS engine and deploying Kubernetes 1.14. And the pod that I'm going to be using for, I'm basically going to dynamically provision volumes. And the pod I'm going to be using to show that it can actually mount those PVs is a SQL Server pod. So here you can see that my master is a Ubuntu 16.04, and I have 2 workers. They're both Windows Server data center. Now I'm going to show the storage classes that are available. So I actually deployed this Azure file storage class earlier. Let's look at what that looks like. So notice that the provisioner is basically in-tree. The reason you can tell that is the naming convention has kubernetes.io as a prefix, which means that it's an in-tree plugin. And let's apply PVC. Looks like I forgot to delete the PVC before. Okay, what I can do is create another Okay, so I created another one because, yeah, okay, so I created Azure 2, file 2. So let's see. Okay, so the second PV got created just now. That's the PV. If you look in, okay, that's fine. Let's also change the pod to use the new claim name. So we just created the two PV and PVC. We saw that the PV got created. Now we're going to see if the pod yeah, okay, so SQL Server 2. Let's look to see what's happening. Yeah, okay, so the pod got created and it's running, which is good. Let's look at the mount section here. So we can see that the mount section here shows that we were able to mount from Azure Volume into C data within the container. And I'm trying to see. So that's basically the PV that just got provisioned in the backend right now. So with that, we can see that Azure file entry actually works today. And I'd like to call John to actually continue with external provisioning and CSI information.
All right, thank you. Just need to switch laptops real quick. All right, so Anusha showed us how entry plugins work. And she mentioned also that external provisioners exist. So external provisioners basically, of course, kube maintainers, you don't want to have every single storage plugin that anyone is ever going to write into the kube code base. That would be bloated. The reviews would be horrible. And so they came up with a first idea to try and make it possible to write out-of-tree storage plugins. And so that was external provisioners. So the basic idea for external provisioners is you have an external process that's running, and when a person volume claim comes in, the person volume controller, if it doesn't know the provisioner that it's supposed to be provisioned by, just flags it, and that's it. It just waits for the external process to can't pick it up and actually provision the volume. And so the external component on the right is the part that actually does that. So the entry plugin at this point delegates the create and delete operations to the external provisioners. And the external provisioner then returns a PV object. And that goes back to the API master. The API master takes care of the attach and detach operations. So the PV object has to be one of the entry ones. And then the mount and unmount volumes can be delegated to a flex volume plugin. Flex volume plugin is really just a process running on the worker. And that's basically the architecture for this new model that Kube came up with. So for Windows, there's really two flex volume plugins today that exist for Samba and iSCSI, Samba for file system and iSCSI for block devices. And I'm going to show you today a proof of concept for dynamic provisioning with external provisioners for iSCSI. And so let's see how that works. So be patient with me because I have to hold my mic at the same time. So I have a very simple Kube cluster. I have a very simple Kube cluster with just a master and a Windows worker. And ahead of time, I deployed an external provisioner to it. So if we go look at kubeget-all, that's the external provisioner that's running. I made the manifest files available on GitHub. I'll give you the link right after if you want to go look at it. But the interesting part is the storage class. So we have this one storage class here that is the storage class that target the iSCSI server that I have running. And if I deploy this manifest, so it's a really simple pod that's running Microsoft Server Core, does nothing, just waits. And it has one PVC. And that PVC references a PVC that's been defined right above. If I can get my SSH to work. There we go. That's the PVC that got defined before. And the important part here is the storage class that we defined. Again, that's going to be in my GitHub, so you can go see the exact details. And if we deploy this, everything got created. I have this new PVC that's pending. Hopefully it shouldn't take too long. Still pending. There we go, it's bound. So it's 100 megs, the capacity requested, the access modes requested. And if we go look at the pods that are running, we have this new pod here, container is still creating, and now it's running. And if I describe this pod, nope, not the way I want, yeah, I guess. If we go look at the mounts here, we can see that we mounted this iSCSI volume onto the pod. Thank you very much. So this shows that you can do today dynamic provisioning on iSCSI on Windows using a slightly modified version of the target deprovisioner that is out there, and using flex volume plugins. If you're interested in the exact detail of the demo, sorry I went a little fast, but this GitHub repo has a write-up that really explains in details how you can do the same. So entry plugins, that was pretty much what started storage in Kube. Then there was external provisioners, but you still don't have that much flexibility. You're still restricted to random binaries being in your workers, being where you expect them, and having a weird contract to fulfill. So that was not really satisfying, and so the Kubernetes community came up with a CSI, which is a standard that defines how plugin should behave in the future. So the model for CSI is basically everything goes to CSI, as opposed to external provisioners, where you still had some part that was in tree. The PV sources needed to be in tree. And for CSI, you just have an external process that listens that needs to register with the Kube API, and then that listens for gRPC messages for all the operations that we care about. So provisioning volumes, creating them, then attaching them to the worker nodes, and then mounting them mounting them on the pods that actually need them. And there's two more operations that are in alpha state right now for backup, for being able to back up running CSI disk, and for restoring that backup. But that's really just alpha support for now. So what a CSI plugin really needs to do, it needs to be able to register itself with the API and the kubelet and the worker nodes. On the worker nodes, it needs to be able to make syscalls to the worker's operating system. It needs to be able to mount volumes on that host that are accessible to other processes on the same host, typically the processes that are going to be running in the pod that you care about. And if you look at the CSI plugin that exists today, they all containerized because you just want Kube to be able to run your stuff. So they're all containerized, and they all pretty much do this operation the same way. So the way they register is using a sidecar that Kubernetes provides. And so they register through a Unix socket talking to that sidecar. To make syscalls to the OS, they need to run in a privilege mode. And to be able to mount volumes on the host that are going to be accessible to other pods, they use mount propagation on Docker. And the problem with Windows is that you don't have privilege support, and you don't have mount propagation. So you can't really write CSI plugins the right way on Windows today. And that's why CSI support for Windows is really very much a work in progress. And Microsoft tells us that privileged mode is not going to be supported in Windows before 2020 at best. And we're still trying to get them to implement mount propagation. So in the meantime, we have to come up with a solution for that. And basically, the two main ideas we have today is either saying, OK, like you can't write CSI plugin in Windows in a container. It's just not possible. You have to do a host process. Or you still can write in a container and somehow work around the problems that we talked about. So these solutions, the first solution is just saying, OK, like sorry, you can't use containers for this. You just have to run a binary that's going to be running on the host. And that comes with a number of problems, because that means you can't register using the sidecar, because you can't talk to the Unix socket of a container from the host. And you also have the problem that you need to somehow get this binary in your workers. That won't be able to be handled by Kube. So you need to package it, distribute it yourself. And the life cycle of the process is going to be independent from Kube too. So you're going to have to somehow make sure it restarts. If it crashes, you're going to have to handle the logs yourself. So that doesn't seem like a great solution. So the second option is to somehow still run containers. So that's cool, because I mean you have Kube there after all. So that's a good way to make sure everything runs and to deploy things. You don't have to reinvent the wheel for that. You can use the register sidecar for this, and all the distribution lifecycle is going to be handled by Kube. And so the problem is, how do you get around the lack of privilege support and mount propagation? Well, there's two ideas for this. The first one is saying, OK, like the CSI plugin itself is going to be an unprivileged container, but as part of Kubernetes, we're going to ship a binary that's going to be basically a proxy for syscalls to the host. So that would be just a raw binary that runs as root on the worker, and that exposes a Windows name pipe that the CSI pods can connect to and make syscalls through that binary. That comes with a number of problems. So the first one would be that, of course, this proxy would have an API that we need to version and maintain backward compatibility across versions, and that sounds painful. And there's also security concerns. You want to make sure that the access to this name pipe is going to be restricted to only the CSI pods, and not any random pods can talk to them. That can be solved in part by our back policies, but there's still more potential issues to think about there. And the second option to say, OK, like we're still going to run in containers so that we can leverage what Kube knows how to do. It's basically a hack saying, OK, we're going to change containerd to be able to pretend that we run a container, to run with all the semantics and the external appearance of a container, but actually just a raw process in the host. So that would be a hack at the containerd level, and that would allow us to use all the goodies that come with Kube. Problems, of course, it's really hacky, and it might result in very poor user experience because you're going to tell you, hey, like this is privileged ship on Windows, and yeah, sure, but it's not a container anymore. So we're not really sure what to do there. There's no real consensus yet. So if you have an opinion and you're interested in this, please do come to SIG Windows community calls or join the discussion there. We have calls every Tuesdays at 9:30 a.m. PST. And while we're in the subject of community, I'd like to thank Deep Debroy from Docker, who's been working hard on this problem of CSI for Windows, and the two chairs of the SIG Windows interest group, Patrick Lang from Microsoft and Michael from VMware. And yeah, in summary, you can use today in-tree and flex volume plugins. You can also use ISO provisioners to some extent, like that's the proof of concept I showed you. And CSI plugins for Windows should happen at some point in the future, but they're not yet. They're not there yet. And yeah, that's pretty much all we have today. Any question? All right.